Hello and welcome to this new video of Math-S400, Mathematics and Economic Modeling. Today we're going to continue our discussion of sequences, and we're going to introduce the concept of a Cauchy sequence. We will see that Cauchy sequences are sequences that converge, and vice versa, any convergent sequence is a Cauchy sequence. But let's start by introducing the definition. Okay, so remember, if we have a sequence xn, it's a sequence of vectors, then we say that the sequence converges to some vector x if the following definition is satisfied, namely that for all epsilon greater than 0 there exists a number big N epsilon such that for all numbers greater or equal to this number the distance between xn and x is smaller than epsilon. Okay, so you say, if I have a sequence of vectors, how do I know that it converges? Well, basically I have to find an x, and then I have to verify this definition of convergence towards x. Now there might be a problem. In many cases you are given the sequence, but you're not really given the value of x. Okay, so if you don't know x, it's quite tricky to verify this definition, right? If you have a sequence and you have no idea where it should converge to, then it's quite difficult to show this definition of convergence. So in some cases you are given a sequence and you would just like to know whether it converges or not without actually knowing the limit of this possible sequence. So in this case you can use the definition of a Cauchy sequence. Okay, so a Cauchy sequence, so again we start with a sequence. We say that the sequence is Cauchy if it satisfies the following definition, and it's quite similar to the definition above, except for some minor differences. So we start with the same. For every epsilon bigger than 0, there should exist a number n epsilon and n, such that for all, and now we have to take two numbers, n and m, greater than this n epsilon, the distance between xn and xm is smaller than epsilon. Okay, so that's the definition of a Cauchy sequence. So basically what this definition says is that if I go far enough into the sequence, then any two numbers that are far enough, for any two vectors in the sequence that are far enough into the future, their distance will become arbitrarily small, right? So any two vectors arbitrarily far into the sequence are arbitrarily close to each other. This is basically what this notion says. So notice that for this definition of convergence we needed to know, or we needed to have an idea of this vector x that it converges to. The definition of a Cauchy sequence doesn't make any notion of a limit, right? I don't know where the sequence converges to if it converges, but I don't need to know it because these are simply elements in the sequence itself. Okay, so it doesn't require the knowledge of the limit of a sequence in order to verify if a sequence is Cauchy. Okay, I will give some examples of how we can use this definition to verify if a sequence is Cauchy or not. But first, you're going to prove a theorem on Cauchy sequences. And the theorem is the following. You have that xn is Cauchy if and only if the sequence xn converges. Right, so the theorem basically says that any Cauchy sequence converges and any convergent sequence is Cauchy. So in order to know if a sequence converges, we can simply verify the second definition, right? Because then it's Cauchy. Instead of writing this entire definition, you will also write this, that the distance between xn and xm, if n and m go to infinity, is going to 0. Or you can also write that the limit for n going to infinity and for m going to infinity of xn minus xm is equal to 0. Right? So these are all equivalent definitions to this definition here of a Cauchy sequence. Okay, so this is an if and only if condition, so we need to go from the left to the right. We have to show that this implies this, and then we have to show that this implies this. So if a sequence is Cauchy, then it converges, and if a sequence converges, then it's Cauchy. So let's first go from the right to the left. So what do we have? We have a sequence that converges, and we want to show that it's Cauchy. So start with xn converges. Okay, so if a sequence converges, we know that it converges to some limit. Okay, so let x be its limit, and because this sequence converges, we know that xn minus x, the distance between these two, converges to 0. Okay. What we need to show is that the distance between xn and xm, alright, these can all be vectors, if n and m go to infinity, is going to 0. This is not so difficult. We can use the convergence lemma that we talked about before. So let's look at the distance between xn and xm, and we would like to show that this goes to 0 as n and m go to infinity. So we can use the trick by adding 0. So we copy xn and we copy xm, and then we add and subtract the same vector. And because we want to know something about the vector x, we're going to subtract x and we're going to add x here. Okay, so this is basically adding 0 vector to this vector sum. And then I have the norm of the sum of two vectors. So by the triangle inequality, I can split it up into xn minus x, distance between these two, plus x minus xm. Okay, I know that xn converges, so this sequence goes to 0. Here also the distance between x and xm as m goes to infinity goes to 0. So if n and m go to infinity, this has to go to 0 too. Convergence lemma that we talked about before. So we have that xn minus xm converges to 0. So xn is Cauchy. Okay, so here the way you have a sequence that converges, we know that the distance between xn and x goes to 0, but we can write the distance between xn and xm is always smaller than the distance between xn and x plus the distance between x and xm by the triangle inequality. You know that this goes to 0, this goes to 0, so this also has to go to 0 as n and m go to infinity. Okay, so this is the easy way of the proof from right to left. And now let's go from left to right. Okay, so what do we have? We start with the sequence at Cauchy, and you would like to show that it converges. So let xn be Cauchy. So we know that this happens, and we have to show that it converges to some limit. Now we're basically faced with the same problem, right? We don't know what the limit of this Cauchy sequence will be, or what could be a. So towards this end, we're going to use the Bolzano-Weierstrass theorem. So remember, this theorem says that any sequence that's bounded has a convergent subsequence. Okay, so if the sequence will be bounded, we can extract a convergent subsequence, and this convergent subsequence has a limit. Okay, and then the only thing that you are left to show is that this sequence converges to the same limit as the subsequence. So we use the Bolzano-Weierstrass theorem in order to get a convergent subsequence and basically to get a limit of this convergent subsequence. So in order to use this Bolzano-Weierstrass theorem, we're going to have to show first that this sequence is bounded, right? Because Bolzano-Weierstrass only holds when sequences are bounded. So let us first show that the sequence xn is bounded. So the only thing that we know is that the sequence is Cauchy. So let's start by writing down the definition of a Cauchy sequence. Okay, so for all epsilon bigger than 0, we know that there exists a number such that for all n and m greater or equal to this number, okay, there should not be 2 points here, it should come here, the distance between xn and xm is smaller than epsilon. Okay, so this is the definition of a Cauchy sequence. So what we're going to do, we're going to simply take a number epsilon and plug it into this definition. Okay, so for example, we could set epsilon to be equal to 1. Okay, so if epsilon is equal to 1, what do we know? Well, we know that there exists a number, now it's n1, such that for all n and m greater or equal to n1, the distance between xn minus xm is greater than 1. Okay, so this holds for all n and m bigger than this number. Right, so in particular, I can set one of these two equal to this number, and then the condition should also hold. Okay, so in particular, I know that there exists an n1 and n, such that for all m greater or equal to n1, xn1 minus xm is smaller than 1. Okay, that's basically what we have. And from this, it follows that xm is smaller than xn1 plus 1. Okay. So how do I get to this last inequality here? Well, it's basically a simple consequence of the triangle inequality. So if I start here, so this is a side note. Okay, so if I start with xm, I know this is equal to xm minus xn1 plus xn1. Okay, I know that by the triangle inequality, this is smaller than xm minus xn1 plus xn1, the norm of xn1. And then because of this, I know that the first term is smaller than 1, and then I have plus xn1. Okay, so this is xm1, xm, x small m is smaller than 1 plus x big N 1. Okay, so this is basically what's stated here. Okay, so this is where I'm at. There exists, if it's Cauchy, then there exists a number such that for all terms further on in the sequence beyond this number, the norm of this number is smaller than the norm of this x of this number plus 1. Okay, so let's write down the sequence. You have a first term in the sequence, you have a second term in the sequence, you have a third term in the sequence, and so on. And then at some point we arrive at the n1th number in the sequence, n1th vector in the sequence, that's just this one, and then I have x n1 plus 1, and so on and so on. Okay. So let's see, the norm of this number here is this. Okay, so the norm of this number is this, and the norm of this number is the norm of x3, and so on. Okay, so I have that finally. This is the norm of xn1, and then for all these numbers, well, I can copy. Let me first write down all the norms, right? So these are the distances, and you have to show that all of these numbers are lower or equal to some fixed number. Okay, so let me call m to be equal to the maximum. It's not on the board, of x1, x2, and so on, until xn1, and then xn1 plus 1. Okay, so m is, this is a number, this is a number, this is a number, and so on. So m is the maximum of all these numbers. Okay, observe that there are only finitely many numbers here, right? So this is a, n1 is a finite number, right? So this is at this position, and then we add one more number, so we're taking the maximum of a finitely many numbers. So this is simply a number in R, right? This is well defined. So here the norm of x1 is clearly smaller or equal to m, right? Because x1 is here, and we take the maximum of this number and some other numbers. So I know that this is smaller or equal to m. Also, the norm of x2 is also smaller or equal to this number, right? Because x2 is here, and I'm taking the maximum of this number with some other numbers. So this is smaller or equal to m. The same goes for the third one, and so on, and so on, and so on. This number is in the list, right? So the norm of xn1 is smaller or equal to the maximum of this number with some other numbers. And then finally, for everything that's beyond this threshold, I have already shown that the norm of these numbers is smaller than xn1, the norm of xn1 plus 1. Okay, and this is at the last position, so I know that all of these are also smaller than m. So, okay, so any element in the sequence has a norm that is smaller than m, and m is simply a fixed number, so I know that this sequence is bounded. Okay, so from this it follows that xn is bounded. Okay, so basically what you have shown is that we started with the definition of a Cauchy sequence. From this definition it follows that from some point onwards the norm of every vector in the sequence is smaller than the norm of the n1 element in the sequence plus 1, right? And this is a finite number. So what do? We take the norm of every vector in the sequence up until this number, and then take the norm of this vector plus 1 as the last one, and we take the maximum of all these numbers, of all these norms. And then you can show that for every vector in the sequence, the norm of this vector is smaller or equal to this number, so the sequence is bounded. Okay, so there's a fixed number that's greater or equal to the norm of any vector in the sequence. Okay, so remember why we did this. We did this in order to show that this sequence is bounded, so we can use the Bolzano-Weierstrass theorem. So we use Bolzano-Weierstrass. Okay, so there exists a subsequence, let's call this x phi n, that converges. Okay, this is something that we have shown in the previous video. So for example, x phi n, let this converge to x. Okay, this is simply a vector in Rk. So we have found a limit of a subsequence of the original sequence. So you still need to show that the original sequence also converges. So we're going to finish the proof by showing that that this original sequence converges also to this same limit here. Okay, so in particular we want to show that xn minus x, that the distance here goes to 0. Okay, so what can we do? Well, we can use the same trick as we always do. We can add and subtract the same number. So add and subtract the same vector in this case. So we take xn minus x, let's take x phi n, right? So this is the nth element in this subsequence here. And then we add the same one. And then we subtract x. Okay, so here we're adding the 0 vector. So we can gather these two, this sum together and this sum together, and then use the triangle inequality. So we have xn minus x phi n, the norm, plus the norm of x phi n minus x. Okay, and let's now look to these two terms. So this is the difference between two vectors in the sequence. Okay, this is the nth element in the sequence, and this is the nth element in the subsequence, so it's also part of the original sequence. So what happens if n goes to infinity? Well, if n goes to infinity, then this vector goes further and further in the sequence, but also this vector goes further and further into the original sequence, right? We're going further along the subsequence, so we're also going further along the original sequence. So this goes to 0 because we have a Cauchy sequence. Okay, remember, any two terms far enough into the sequence come closer and closer together, right? They converge to 0. So by the definition of Cauchy sequence, this difference will go to 0. And now here we use the fact that this subsequence converges to 0. So if n goes to, this will also converge to 0. Okay, so xn minus x is smaller than the sum of two sequences that go to 0. So by the convergence lemma, we have that xn minus x also goes to 0. Okay, and then this finishes the proof. Okay, so this shows that any convergent sequence is a Cauchy sequence, and any Cauchy sequence converges. So remember, along the way we showed that a Cauchy sequence is a bounded sequence. Okay. So basically we have already a result following from this that says that any sequence, no, I should say any convergent sequence is bounded. Okay, so why is this? Well, we know that any convergent sequence is Cauchy, and in the proof we have shown that any Cauchy sequence is bounded. So any convergent sequence is also bounded. Okay, so let's take a small break. Okay, welcome back. Let me now show two examples in order to illustrate the concept of a Cauchy sequence. So let me first look at this particular sum. So I take the sum from t1 to some number n of 1 over t squared. Okay, and the number that I get from this, I call this xn. Okay, so I have the sequence x1, x2, x3, and then the question is, does xn converge? Okay, so in order to answer this, with the original definition of convergence, we would have to have an idea of the limit of this sequence of xn's. Okay, so for example, if n is equal to 1, then I have the number 1. The second element in the sequence will be 1.25. The third element will be 1.36111 or something, if my calculations are correct, and the fourth element will be 1.423, and so on and so on. Okay, so in general, there's not really a clear limit to this sequence. At least I don't see it. However, I still want to show that this sequence it has a limit. It converges. Okay, so in order to do this, I can still use the concept of a Cauchy sequence. Okay, so the only thing I need to show is that xn minus xm, that this goes to infinity as n and m go. This goes to 0, sorry, if n and m go to infinity, right? For bigger and bigger n and bigger m, for any n and m that are big enough, this goes to 0. Okay, good. So let's see what this gives us. So we have xn minus xm. So let's just plug in the definition of. Actually, I should not. It's not necessary to take the norm because these are simply numbers, so I can take the absolute value. So xn, just plug in the definition here. So this is the sum from t equal to 1 to n of 1 over t squared, and then I subtract the sum of t equal to 1 to m of 1 over t squared. Okay. So let me assume, and this is without loss of generality, that, well, either n is bigger than m or m is bigger than n. Okay, so let me take n greater or equal to m. Okay. So what do I have? Here I have a sum from 1 to n, which is a bigger number than m. And here I subtract the sum from 1 to n. Okay, so what I'm left with is a sum from equal to m plus 1 to n of 1 over t squared. And 1 over t squared is non-negative, so this is simply tn plus 1 to n of 1 over t squared. I can get rid of the absolute value here. Okay, and now comes a little trick. Okay, so we know that t squared is greater or equal to t times t minus 1. Okay, because t is bigger or greater than t, and t is greater or equal to t minus 1, so t times t is greater or equal to t times t minus 1. And then of course, if you take the reciprocal, we have to switch the inequality sign, so this is smaller than t times t minus 1. Okay, so this is lower or equal to t equal to m plus 1 n 1 over t times t minus 1. And then 1 over t minus 1 is the same as 1 over t minus 1 minus 1 over t. This is the same. Okay, so put it on a common denominator, then you have here a t, and you get minus t minus 1, so you get a 1 as a result. So this is a simple identity. So we can write this as the sum of t equal to m plus 1 to n of 1 over t minus 1 minus 1 over t. Okay. So let's write down explicitly the sum. Right, so the first term, t is equal to m plus 1, so this gives you 1 over m. And then the second term will give you minus 1 over m plus 1. The second term in the sum, t will be equal to m plus 2. Okay, the next one. So 1 over t minus 1 will be equal to 1 over m plus 1. And then you have to subtract 1 over m plus 2. And then the third term will be equal to 1 over m plus 2 minus 1 over m plus 3. and so on. And then finally the very last term will be equal to 1 over n minus 1, and then we subtract 1 over n. Okay, and you see each time we have minus a number and plus a number here. You have minus a number and plus the same number here. You have minus a number and plus the same number will be the next one here. Right, so we can each time add and subtract the same number, and then we subtract this number and add the same number here, and we're left with this one. So this entire summation is nothing else than 1 divided by m minus 1 divided by n. Okay, and this is negative, so this is less or equal to 1 over m. So we have to show that this goes to 0 if n and m go to infinity. So here, if m goes to infinity, we see that this converges to 0. Okay, so if n and m go to infinity, this goes to 0. This is smaller than something that goes to 0. So we conclude that xn minus xm also converge to 0. In other words, this is a Cauchy sequence, so it converges. So this is how we can use the concept of a Cauchy sequence in order to show that a sequence whose limit we have no idea about actually is a convergent sequence. Now let's take a second example, and here it's again a sum. We sum t equal to 1 to n, and now we don't take 1 over t squared, but we take 1 over t. Okay, and we call this sum to be equal to xn, and we would like to know does xn converge. Okay, so for example x1 will be equal to 1 here, the second element will be 1.5, the third element will be 1.8333, the fourth element will be 2.083, next one will be 2.2833, and so on and so on. So it's clear that every element will be somewhat bigger than the one before, because you're adding 1 over t to the sum. But now the question is, does this converge, or does this not converge, right? Does it go to infinity maybe? And it turns out that in this case it actually doesn't converge, right? So it doesn't have a limit. The sequence xn of sums, of these sums, doesn't have a limit. And we're going to show this by showing that the sequence is not Cauchy. Okay, so you know that any Cauchy sequence converges, and any convergent sequence is Cauchy. So if you take the contrapositive, you know that if the sequence is not Cauchy, then it doesn't converge, right? So in order to show that it doesn't converge, you can also show that it's not a Cauchy sequence. Okay, so remember the definition of a Cauchy sequence is the following. For every epsilon bigger than 0, there exists a number n big N such that for all nm greater or equal to this big N, xm minus xn is smaller than epsilon. In case of numbers, and otherwise we have to use the norm and vectors. So we would like to show that it's not Cauchy, right? So we have to negate this formula, and you have to show that the negation of this formula is true. So let's negate this formula. We have to show that there exists an epsilon bigger than 0, such that for all n and n, there exist numbers n and m greater than this big N, such that xm minus xn is greater or equal to this epsilon, right? So we have to find an epsilon such that for any number that we take, we can find two numbers such that the distance between these two numbers is greater or equal to epsilon. Okay, so let's try to do this. So we take xm minus xn, and we have to show that it's bigger than some number, right? We can always find an m and n. Okay, that satisfies this, and it's bigger than some number epsilon. Okay, so let's plug in the definition of xn and xm. So here we have xm as the sum of t equal to 1 to m of 1 over t, and then xn is the sum of t equal to 1 to n of 1 over t. And as in the previous one, either m or n is bigger. Without loss of generality, we can assume that n is greater or equal to m. Okay, the other n greater or equal to n will be perfectly analogous. So what do we have? We have the absolute value of the difference of two sums. This one goes from 1 to n, and this one goes from 1 to n. Okay, so what we are left with is going to be the sum from n plus 1 to n of 1 over t. Okay. We can drop the absolute value because this is the sum of non-negative numbers. 1 over t. So let's write them out. We have 1 over n plus 1. We have 1 over n plus 2, and so on, plus 1 over n. Okay, so this is the last one. Now we have to put this greater or equal to some number epsilon, right? So whatever inequality that we have here, we want it to be a greater or equal than inequality. Now this is a sequence of sums. So which one is the smallest of all of these? Right, this is n plus 1, n plus 2. The denominator always increases, so this is the smallest one. Okay, so what we can do is you can say that the first one is greater or equal to 1 over n, the second one is greater or equal to 1 over n, and so on, and the last one is greater or equal to 1 over n. Okay, so here we have a greater or equal sign. How many of these fractions do we have? Well, we have in total n minus m of these terms, so it's n minus m divided by n. And this is 1 minus m over n. And you have to show that it's greater or equal to some number, epsilon, right? So we have to show that for every big N, I can find two numbers that are greater than this number, such that this distance is greater than some epsilon. For example, what we can do, so here we can take any two numbers bigger than some number, right? So for example, we can set n to be equal to 2 times m. Okay, if I have chosen n to be greater than m, I can pick any n and m that I want. My particular choice is to set n to be equal to 2 times m. So what do I get when I use this value? Well, then I get 1 minus m divided by 2m is equal to 1/2. Okay, and I put epsilon to be equal to this 1/2. So what I have done is there exists an epsilon, yes, exactly this epsilon, 1/2, such that for all numbers I can find two numbers n and m bigger than this number. Well, in particular, I chose n to be equal to 2 times m. That's okay. And then the distance between xm and xn, right, which we have here, is greater or equal, right, so we have a greater or equal here, 1/2, which is equal to the epsilon that I have chosen. So this shows that this sequence of sums does not converge. In particular, it will go to infinity. So if you want to know more about the sequence, this is called the harmonic sum. Right. And it's a well-established mathematical fact that the harmonic sum does not converge, right? It goes to infinity. Although the term that you add will get smaller and smaller and smaller every time, this entire sum does not converge to any number. To finalize this lecture, I would like to introduce and prove one lemma. This is a lemma that we will use later on in the course, and it's the following. So take a sequence in Rk, it's a sequence of vectors, and then we have the following fact. this sequence converges to some vector x in Rk, if and only if every subsequence of the sequence has a further subsequence that converges to this vector. Right, so you have to imagine you take any arbitrary subsequence of this vector here, then this arbitrary subsequence should have another subsequence, so this is a subsequence that actually converges to this x. Okay, so here we have an every, so this is basically a for all, right? So for all subsequences of xn, there exists a subsequence, right? This is how we can call it, that converges to this x. Okay, so the power of this theorem is basically in the for all, right? Because this has to hold for every subsequence that you can think of. You need to find another subsequence that converges to x. Okay, so this is an if and only if statement. So let's prove this. So we have to go from the left to the right and from the right to the left. There's one way that's very easy, and that's from the left to the right, right? So basically, if the sequence converges to x, well, what do we know? Well, we know that every subsequence of this sequence also converges to x. Okay, and then every subsequence of this subsequence, right? So every subsequence then of course also converges to x, right? Because if you just take further and further subsequences, all the limits of all these subsequences have to go to the same vector x. Okay, so if the vector x converges to x, then every subsequence converges to x, and of course this subsequence has a subsequence that converges to x, right? Take any arbitrary subsequence of this subsequence and it will go to x. So I will simply put from left to right, it's easy. And now go from the right to the left. So we have to show that if every subsequence of xn has a further subsequence that converges to x, then the original sequence also converges to x. And we're going to use a proof by contrapositive. Okay, so if this is P and this is Q, you want to show that P implies Q. Contrapositive is done by showing that negative Q implies negative P. Okay, remember, you negate the both formulas, but then you have to change the direction of the arrow. So these two things are equivalent, so we're going to show negative Q implies negative P. Okay, so let's start by negating this. If the sequence does not converge to x, right, this is basically what it means. So negative Q is xn does not converge to x. We need to show negative P, right? So we have to negate this. So this, remember, this is for all subsequences of the sequence. There is a further subsequence that converges to x. So if you negate, we have to change the for all into an existence, right? There exists a subsequence of xn. Okay, and this has to become a for all, such that for all, let me call this now subsequences, right? So this is then a subsequence of this subsequence, right? For all subsequences. Here the premises is that the subsequence converges to x, so the subsequence does not converge to x. Okay, so restating, what do we need to show? We need to show that if the sequence doesn't converge to x, then I can find a subsequence such that any subsequence that I take of this subsequence, this subsequence will not converge to x. Okay, so this is what we're going to prove. So xn doesn't converge to x. Well, we know the definition of convergence. For all epsilon, there exists an n epsilon and n, such that for all n greater or equal to this n epsilon, xn minus x is smaller than epsilon, right? But xn doesn't converge to x, so I have to negate this formula. Okay, so if I negate the formula, I get that there exists an epsilon bigger than 0, such that for all n epsilon and n, there exists an n greater or equal to this n epsilon, such that xn minus x is greater or equal to epsilon. Okay, so there is an epsilon, such that for all numbers, so these numbers don't longer depend on epsilon, right, because they have to hold for all numbers. There exists an epsilon, such that for all numbers I can find something bigger than this number, such that the distance from xn to this number is greater or equal to this epsilon. Okay, so I know there exists some epsilon that satisfies this definition. So we can take this this epsilon. Okay, and now then I have that for all n and n, there exists an n greater or equal to this big N, such that xn minus x is greater or equal to this epsilon. So what we're going to do is we're going to create a subsequence using this definition. We're going to use this definition to create a subsequence that satisfies this condition that any subsequence of this subsequence doesn't converge to x. Okay, so how are we going to do this? Well, we're just going to plug in numbers for this big N here, and this will generate me a subsequence. So how is it going to work? So for example, we can start by putting n big N equal to 1. Okay, well then I know that there exists a number bigger than 1, sorry, right, because n is equal to 1, such that xn minus x is greater or equal to epsilon. Okay, so this n that satisfies this condition, let me call this to be the first element of my subsequence, right? I know that there is a number bigger than 1 such that this is satisfied. This xn that satisfies this is going to be the first element of my subsequence. So I know that the first element of my subsequence is going to satisfy this condition. Okay. Next time I'm going to put n to be equal to, let's say, this number here that I found, phi1, and I'm going to add 1, right, just to make it bigger into this sequence. Well, I know that this holds for every n, so in particular it also holds for this particular value of n. So I know that there exists a number that's greater than phi1 plus 1, such that the nth element in my sequence is epsilon far away from x. Okay, so I know that there exists a number bigger than this number that satisfies this condition. Well, I'm going to use this as the second vector in my sequence. Okay, so phi2 is going to be this particular element that satisfies this condition. And I know that x phi2 minus x, of course, satisfies this condition, right? Because that's how n is defined. So I know that this is greater or equal to epsilon. And now I'm going simply to iterate this over and over and over, right? The next time I set phi n begin to be equal to phi2 plus 1, then I know that there is an n greater or equal to this number, such that its distance from x is greater or equal to epsilon. I'm going to set the third element in my sequence to be equal to this number here that satisfies this definition. So I know that x phi3 minus x is greater than epsilon. Next time I'm going to put n equal to phi3 plus 1, I'm going to define phi 4, and so on, and so on, and so on. All right, so after t iterations, I will have that n is equal to phi t plus 1. Then I know that there is an n greater or equal to this phi t plus 1, such that xn minus x is greater or equal to epsilon. And I'm going to set phi t plus 1 to be equal to this n that satisfies this. And then I have x phi t plus 1 minus x, of course, satisfies this definition, so its distance is greater than epsilon, greater or equal to epsilon. And I can continue doing this forever, right? Because the sequence never ends. So I can always find, set n equal to this number, always find something that's further away that's greater or equal to epsilon, and so on and so on. Okay, so if I do this, then this procedure generates a subsequence. Okay, this is a subsequence of xn. Now, what do I know about the subsequence? Well, I know that the first element of the subsequence is epsilon far away from x. The second element of the subsequence is also epsilon far away from x. Third element is epsilon far away. The tth element is epsilon far away. Any element or any vector in the sequence will be at least epsilon far away from x. Alright, so for all n, I know that x phi n minus x is going to be epsilon far away from x. Okay, so if I have x here, I can draw a ball with radius epsilon, and then every element in the subsequence has to be outside this ball of radius epsilon around x. So I have created a subsequence, right? This is the subsequence I created, this x phi n. And I have to show that every subsequence of this sequence does not converge to x. Well, this is obviously true, right? So if I take a subsequence of the sequence, then it will always be epsilon far away from x. So it's impossible to converge to x, right? So any subsequence of the sequence can never approach x closer than the distance epsilon. Okay, so no subsequence of x phi n can converge to x, and we're done. Okay, so that's the end of this lecture. Hope to see you next time.